Number 8. Complete the following problem without using a calculator. So we're going to use calculus here to complete this. Given this function, find the critical values. So critical values occur when the derivative is either equal to 0 or does not exist. Okay, so right down here I'm going to take the derivative. I've got f of x is equal to 2x cubed minus 9x squared plus 12x. Take the derivative, f prime of x, 6x squared minus 18x plus 12. Okay, I'm going to see, first of all, does it not exist? Well, it's just a polynomial. Polynomials exist everywhere. We're good with that one. So now I'm going to set it equal to 0. And I'm going to notice everything has a 6 in it, so I'm actually going to divide them all by 6. X squared minus 3x plus 2. This is going to help me solve it because now I can factor it. X minus 2, x minus 1. This gives us the values of 2 and 1. Alright, we want to know where f is increasing and decreasing. Well, that's tied directly to the derivative. Okay, so we're going to take the derivative and these two values that we got from setting the derivative equal to 0. And honestly, they should be the other way around. I don't know why I did that. Okay, 1 and 2. And we are going to put them on a number line and check them in f prime of x and see what's going on. So if I check a number to the left, 0, don't forget I'm checking it in f prime of x, so that's right up here. I want to know if I plug in 0, this will be negative 2, this will be negative 1, negative 2 times negative 1 is going to be a positive number. Let me check a number in between 1 and 2. If I plug in like 1.5. 1.5 minus 2 will be negative, 1.5 minus 1 will be positive. Negative times a positive is negative. Plug in something like 3. 3 minus 2 is positive, 3 minus 1 is positive. That's a positive answer. So our function is increasing when the derivative is positive. So we're increasing from negative infinity to 1 and 2 to infinity. And we're decreasing in between 1 and 2. Alright, let's go back, look at C. Now we want to do relative max. Well, a maximum on a graph is when we have to go up and then go down right afterwards. Positive first derivative, negative first derivative. Whoa. Up, down, right? So where does it go from positive to negative? That occurs when x equals 1. Relative min occurs when the opposite happens, when we go down to a point and then we go up afterwards. That would make it a min. So that's a negative first derivative, positive first derivative, and that occurs when x equals 2. All right, how about the absolute maximum value? And now they give us an interval. Okay, so, well, we've identified a possibility, right? We've identified 1 as a possibility. And now they've given us 2 other options. Those are the endpoints, 0 and 3. We got 1 through our derivative check, and the other 2, the endpoints, could also be maxes. So we have to plug these values into our function to see which one literally has the biggest value, which is what we're asking right here. So let's plug them in. We've got 0 is really easy. That gives us 0. 1's not so bad. It's 2 minus 9, which is negative 7, plus 12, which is 5. And now let's plug in 3. That one's a little bit messier. We've got 2 times 3 cubed, so 2 times 27, minus 9 times 3 squared, which is 9, plus 12 times 3, which is 36. So 2 times 27 is 54, minus 9 times 9 is 81, plus 36. If I see here, 54 and the 36 is actually 80 and 90. That's bigger than 81. Specifically, that's going to be 90 minus 81 is going to be 9. So 3 is actually the absolute maximum value. All right, section E. Where does f have an inflection point? Anytime you see the word inflection, you should think second derivative. So let's go back to our first derivative. Actually the first derivative, not the one I simplified, the first derivative. And that was 6x squared minus 18x plus 12. And take its derivative to get the second. That becomes 12x minus 18. We have to see where this does not exist or is equal to 0. It exists everywhere because it's just polynomial. So let's set it equal to 0. Add 18. Divide by 12. And we get 3/2 equals x. Okay, so now we want to see, is this actually an inflection point? Because right now it's just a possible inflection point. 3/2. We do the second derivative test. Plug in a number to the left. And we're plugging this into the second derivative. So I'm going to plug in 0. That's negative. Plug in a number to the right, maybe like 2. 12 times 2 is 24 minus 18. That's positive. So this is a point of inflection. POI, as we said in class. Where's it concave up and concave down? Well, we've already done that test. Concave up is positive first derivative. Concave up equals from 3/2 to infinity. And concave down is up until 3/2, so negative infinity to 3/2. All right, done with problem number 8. Moving on to problem number 9. It's a little bit different. It's a chart. We have selective values of h, so these are values of the function. The second derivative is bigger than 0, which means concave up, which basically means that, it looks like something like this, right? And since we have these values right here, and we can see the function is getting bigger, really it's concave up and increasing, so it looks like that side. And we're asked to use the values to estimate the value of the first derivative at 3. So the derivative, we had learned the derivative, h prime of x, is really the slope. And since these are like basically x and y values, we can find out slope the old way. And we want to know what the slope is at 3. So really, we can't use just 3. We could find the slope between 3 and 2. We could find the slope between 4 and 3. And then we could average those two answers and get the slope at 3 specifically. So that's what I'm going to do. So I'm going to find the slope between 2 and 3 by just using the old method, y2 minus y1 over x2 minus x1. 2 minus 1.4 is 0.6 over 1, so that's just 0.6. All right, let me look at the slope between 4 and 3, or 3 and 4. I probably should have written the other way, but it doesn't make a difference. That's y2, 2.8, minus y1, 2, over x2 minus x1, which is actually 0.8 over 1, or 0.8. So now I can actually average these two. We're saying the slope to the left of 3 is 0.6, to the right of 3 is 0.8. So we would expect, because of this concavity, we would expect our slope to be right in between there. So actually, and it probably will be, we're going to average them. 0.6 plus 0.8, divide that by 2, because we're comparing two slopes, is 1.4 over 2, or 0.7. And that is good because it's right in between, so concavity tells us it's increasing, and the rate of change is increasing, which it is.